Assalamu alaikum. This is Azhar Ali along with Ali Nisar Shah. We will be presenting a lecture today on aerial robotics. In this lecture, we plan to talk about aerodynamics as a branch of dynamics, what is a fluid, application of aerodynamics, why do we study aerodynamics, and why is it important. Then we talk about the crux of this lecture, about the four fundamental forces that act on a body while it's in flight or it's moving in a fluid. That fluid can be either a liquid or a gas or air, but we will restrict our discussion to the objects flying in air only. So aerodynamics. Aerodynamics is a term made up of two words, as we can see. One is aero, another is dynamics. Now dynamics we know is a branch of mechanics which talks about the motion of bodies with reference to the force. So in simpler terms, in dynamics we talk about the motion of objects along with the cause of the motions, as into how the motion is being caused or what is causing the motion. So that's about dynamics, and aero simply means air. So in aerodynamics, it's a branch of dynamics then, where we talk about the motion of objects in air and the forces that cause this type of motion, or whatever type of motion is required in this scenario that we deal under the topic of aerodynamics. So more formally, aerodynamics is a branch of dynamics that deals with the motion of air and other gaseous fluids, and with forces acting on bodies in motion relative to such fluids. So again the same thing. We'll talk about the motion of objects in air and how they interact with the environment, the air, and how multiple forces come together to cause this type of motion. The term aerodynamics is generally used for problems arising from flight and other topics related to the flow of air. Moving on, this is a visualization that explains how aerodynamics work, and this also serves as a motivation why we are studying this topic. In the first picture, which is in green, we can see an aircraft with a particular shape, right? And in the later picture, which is in red, we can see a differently shaped aircraft, right? And these blue arrows are essentially showing us the flow of air, right? So we can see that in the first picture, the shape of the aircraft is such that the air is blowing over it and not resisting the motion of the aircraft very much, therefore causing very less resistance to the motion of the aircraft. And in the second picture, we can see that the air is directly impacting or acting perpendicular to the body of the aircraft, and in such a case, the air resistance or the drag force, more formally we'll define that later on, the drag force is greater as compared to the green picture or the aircraft in green. So such a shape which offers less resistance to air is called an aerodynamic shape. It is more suitable because it minimizes the resistance to the force applied by the engine or the thrust generated by the engine, which tries to move the aircraft in the forward direction. However, in the second case, the red aircraft it's said to be non-aerodynamic. Its shape is said to be non-aerodynamic because it does not stops the it does not minimizes the flow of the force of the flowing air, which is a resistive force, as I said, or which is called drag more formally. Now we will talk about what is a fluid. So a fluid is a term which can be used for something that can flow, right? So fluid is a substance that can flow, and it can take the shape of the container it is contained in. And the physical property of a substance that enables it to flow is called fluidity, right? So there are three type of objects we see around in the matter we see around is in three states basically. One is solids, liquids, and gases. Solids we know are have a definite shape, and they do not flow, right? A chair that is placed by your side does not start to flow all of a sudden, right? Your mobile phone on your table in front of you does not start to flow suddenly. But imagine a glass of water when spilt, the water starts to flow in a particular direction. It continuously moves. So this property which allows the water to flow is called its fluidity, right? Some materials have high fluidity and some have low. Same is the case of air, right? Air often blows from one point to another, or we can say it flows. So air is also considered as a fluid. So liquids and gases, including air, are all considered as fluids. Now, so there's a branch of dynamics called fluid dynamics, which deals with the dynamics of fluids in general, and there's a special branch of it, aerodynamics, which deals with a particular type of fluid, which is the air, which we are discussing here. Now, the more technical thing we are supposed to discuss here is this definition. It's rather a property of fluids, which says that when a tangential shear stress is applied on the surface of a fluid, the fluid will experience a continuously increasing deformation, unlike a solid object, right? I hope it makes sense that when a solid object, when you apply some stress, some force on it, the deformation is not continuously increasing, right? And about this term tangential shear stress, if someone wants to ask, we'll clarify this later. So that's about it. We will discuss this in further detail with the help of visuals and some equations later on in this lecture. Now moving on to application of aerodynamics. So by now the discussion might have made you think that airplanes are probably the only application of aerodynamics, because these are the objects which we often see flying or flowing in the air. But that's not the case. Aerodynamics is important and worth care in so many other scenarios and real life applications. So for example, airflow over an automobile, right? So when an automobile walks or moves on the road, it also experiences aerodynamic forces. Though the forces are maybe not strong as in the case of an airplane, which is of more concern as compared to the automobile, but there are these forces, and having an aerodynamic shape for a car also might help increase its efficiency. Similarly, the gas flow through an internal combustion engine powering an automobile, it is also affected by the effects of aerodynamics, whether in a storm prediction, the flow of an airflow through a windmill, right? So these all of these things are all of these things work in an environment where air is blowing, right? So making their shape such that it is able to perform its task better when the air flows through it, is of much concern, and that's why we study aerodynamics. Similarly, this is the application of the aircraft, the production of thrust by gas turbine jet engines and rocket engines. It also hints towards the application of aerodynamics in aircrafts. Right now, why aerodynamics? Why should we study aerodynamics? Because this is supposed to be a robotics lecture. Why are we talking about aerodynamics? So, as we said, this is about aerial robotics, and in aerial robotics, we talk about robots that are flying, right? Flying in air. And oftentimes, when we talk about robots, we are very much concerned about the environment of the robots. So how a robot interacts with its environment is of very much importance, because we need to know how a robot interacts with the environment. Essentially, there are cameras and other sensors that give the robot information about the environment. Similarly, in aerodynamics, um, we need to understand how the air is blowing, what effect it is posing to the robot which is flying. We need to understand all of these things, and we need to understand how to design our robot in such cases, for such an environment, as we care about the environment in normally in the robots that stand on their position, or that move on the surface. So robotics and aerodynamics are seemingly two distinct fields, but they converge in areas like aerial robotics, where aerodynamic principles are crucial for designing, controlling, that is an important thing, we'll discuss this later, and optimizing the performance of robotic systems. So let's come here. Now, let's talk about drone design. These are the very common aerial robots we often talk about. Aerodynamics plays a crucial role in the design of drones, understanding airflow, lift, drag, and the stability. As I said earlier, these are the forces which we'll just talk about in the later slides. These are the forces which act on an object that flies in the air, and we need to understand these forces and how they what impact they have on the robot in order to make the design better and make our robot fly efficiently, right? Similarly, flight control systems in controls, when we try to when we want to control a system, what we need to understand is the input variables and the output variables, right? So input variables in an aero in an for an aerial robot and or an aero in an aerial robotic system are the forces that the air applies on the robot, right? So in order to control the robot, we must need to study these forces. What impacts do they have on the robot? How do they impact the motion of the robot? So that we can control the robot, right? That's why understanding aerodynamics is really important for designing flight control systems as well. A more practical example would be this type of a drone, which is a delivery bot essentially. So it flies and delivers objects from one place to another. And so in this particular case, we need to understand the capacity the drone can handle, and for that we also need to understand the other forces. For example, if a strong if this robot is on its delivery, and a start wind comes in between, so what should the robot do, and how will it handle its motion? So we need to ensure that it does not falls on the ground, and it manages its motion and keeps itself in control when such circumstances happen, right? That's why studying aerodynamics is essentially important. Lastly, we'll talk about the important forces as we have been discussing. So there are four forces that act on a object while it's in air. These are gravity, thrust, lift, and drag. Here are these, right? Out of these four, gravity and drag are the resistive forces. They act opposite to the motion generated by engines, or to the motion that is desired. So, for example, if you look at this picture, thrust is the force that is generated by the engine to move the aircraft in the forward direction, but the drag due to the air acts in the opposite direction. And similarly, lift tries to lift up the aircraft or keep it in the at least stable at a certain height. Then the weight is the force that opposes this lift force. And here's the summary of how these forces interact, how these forces come into play. Is when lift is greater than the weight, the plane rises, right? It's simple to understand, I believe. If the upwards force is greater than the downwards force, then there's a net force in the upward direction, and hence the aircraft should move up, or in the opposite case, it should move down, as listed here. And similarly, in the third case, if the thrust is greater than the drag, then the aircraft will move forward, or in the opposite case, it will slow down. Okay. So now we'll be talking about we'll be talking about the first two forces here, and the later two forces will be explained later. Gravity is, I think, quite simple to understand. It's just the weight of the object it's the force with which Earth attracts any body towards its center. So it's quite simple to understand. It will be just the weight of the aircraft. Now let's talk about thrust. So thrust is a mechanical force which is generated by the aircraft through its engines. And there are generally two ways this force is generated. One is by the propeller, and other is the gas engines which generate this thrust. So we know that there's fuel in the engine, which when combusted expands or accelerates into towards the backwards direction, right? If you have ever seen a rocket flying above, then the gas burns, and and expands in the downwards direction in that case, and as a reaction of that force that the gas is applying in the downwards direction, or in the case of a aircraft in the backwards direction, there's a reaction force generated in the forward direction, which is called thrust. It allows to move the aircraft in the forward direction, right? The engine does work on the gas, and as gas is accelerated to the rear, the engine is accelerated in the opposite direction, that is the forward direction. This force is called, this acceleration produces essentially, this acceleration is because of a force which we call as thrust. Another way the aircrafts generate their thrust is using a propeller. So here is an example of such a case where there's an aircraft and there's a rotor at its nose, and when the air strikes it, it starts to rotate, and as the rotation occurs, the static air pressure at the face of the rotor is lower than at the back of the rotor. And in such a case, there is a thrust generated in the forward direction, because the static pressure behind the rotor is lower than the is greater than the pressure at the face of it, right? So these are two ways aircrafts normally generate their thrust force. Now over to Ali Nisar.
Now, before we talk about lift and drag, we need to know about some nomenclature. As done in a typical aerodynamics course, we pick a two-winged aircraft as a basis to discuss the basics of aerodynamics. These discussions can, of course, be explored further for any kind of aircraft like helicopters, drones, and more. Now, an aircraft, like the one on the right, has wings that allow it to fly. When we take the cross section of a wing, propeller, or tail, we get the airfoil, which is a cross sectional shape of that respective part, which is designed to produce desired flight characteristics. One such airfoil is shown on the left. This airfoil is of a wing, similar to the one of an airplane on the right. To obtain these desired flight characteristics, the engineers can modify a few parameters in the airfoil design. Let's talk about some of them. The front and back edges are called leading and trailing edges. Of course, the thickness of the airfoil. A line that passes from the leading edge straight to the trailing edge is called the chord line, and the line that goes between the body, right here, between the mean of the any two sides of the body, is called the mean camber line. When a wing is in contact with moving air, either in a wind tunnel or in flight, the wind is called free stream, and its velocity is denoted as free stream velocity. The image on the left shows a free stream going from left to right, and the image on the right shows a free stream or shows a free stream coming at an angle to the wing. Note that these multiple the velocity field can be can be compressed into a single represented as a single vector denoted by v infinity. The angle formed between this vector and the chord line that we discussed in the last slide is known as the angle alpha, or the angle of attack. These are important parameters that determine the lift and drag, which we will now discuss. So, what exactly is lift and drag? When any force acts on the wing, let us denote it by R here, it can be broken into two components. One, lift, that is perpendicular to the free stream, like here, and the other is the parallel component to free stream, which we denote as drag d. If the wing moves in a fluid, that is a gas like atmospheric air, we call these forces aerodynamic forces. If it were water, we would call these hydrodynamic forces. Let us first talk about generation of lift, how lift is actually generated. Keep in mind that there are only two sources of any aerodynamic force being acted on an object by a fluid. Here, by aerodynamic forces, we are talking about lift or drag. One is pressure stress distribution, and the other is shear stress distribution. Both of these forces act on the body's surface. Let's first talk about shear stress. Now, when any wind hits the wing, wing, it causes a frictional force tangential to each point of the wing, of the surface of the wing. This causes a stress which we call shear stress. And another type of stress which is perpendicular to any point of contact is pressure stress. This is caused by pressure distribution. This is a pressure distribution plot where you can see that the pressure below shows the arrows below show points of low, so high pressure, and the arrows above show a point of low pressure. We know um, from a basic mechanics class that in, for example, thermodynamics, high temperature objects release energy towards cold areas of towards cold areas. In a similar manner, high pressure high pressure areas push things towards low pressure areas to equalize. In this case, the wing will lift upwards. Now, as we saw that lift is a resultant of true stresses, and lift itself is in the direction perpendicular to any fluid flow. What we can do is integrate these stresses in the lift's direction, which is perpendicular to the uh, uh, to the wind, for example, as shown by these background lines. We get lift force. As we can see in the formula, minus P is representing these uh, pressure vectors, and tau omega is representing these tangential shear stress vectors. When we integrate this over the entire surface area of the body, in the direction of lift, we get the lift force. Now, one important thing to note is because the shear stress is almost perpendicular to the lift direction, it almost plays a negligible role towards the force calculation of lift. So we can, in most cases, ignore it. Now, here's another thing. The vectors here, like p and tau omega, are actually difficult to calculate. So what we do is use another formula, which is the lift force formula or lift force equation, as famously known, with density, velocity, area, and the coefficient of lift. Through these four parameters, we can find the lift force easily. These can be determined by using standard designs or through experiments in a lab setting or in a wind panel. The coefficient of lift is different for every design of an airfoil. The standard designs have pre-calculated values which simplify the working. Or if a new design is produced, we can calculate this coefficient accordingly. Now, let's talk about drag. Drag, as we discussed before, acts in the direction parallel to fluid flow. Similar to how we calculated lift, we can calculate drag by integrating all the stresses in the direction of the drag force over the entire surface of the wing of the body, which we can symbolically represent as this formula. Also note, similar to how we found problems in calculating drag this way, there's a Similar to how we uh, found problems in calculating lift, we also find it harder to calculate P and tau omega. So there's another formula known as the drag equation, similar to how we saw it in lift, that we can use to calculate drag easily and experimentally. Drag can be further classified into two types: pressure drag, which corresponds to pressure stresses, and friction drag, which corresponds to shear stresses. Unlike what we saw in lift, which was primarily because of the pressure stresses, drag drag constitutes both, whereas lift primarily was just pressure stress. Now that we have talked about both lift and drag and how they are generated, let us look at how a wing achieves flight. We focus on three phases: takeoff, cruise, and landing. First, take a look at the top right image, which compares a cambered airfoil to a symmetric airfoil. The difference between them lies in how they are shaped. A cambered airfoil is, in other words, slightly, while a symmetric is symmetric about an axis. And as you can see, if we denote C as lift and alpha as the angle of attack, a cambered airfoil at 0 degrees angle of attack still produces lift, while a symmetric has 0. So, in other words, if we want to produce the same amount of lift as a cambered airfoil, a symmetric airfoil will have to be tilted or have a positive angle of attack compared to 0 of the cambered airfoil. Each of them have their own benefits and different kinds of planes use them. For example, a symmetric airfoil is mostly used by stunt planes, which sometimes fly upside down, in which case you would not want a lift produced if there is 0 angle of attack. But in a regular aircraft or a commercial airline, you would want as much lift as you possibly can without increasing the angle of attack, because as you increase angle of attack, there is an increased drag produced with it. But before talking about that, let us see this plot, which shows how the angle of attack is plotted against uh, how the angle of attack affects the lift produced for a camber airfoil. As you can see, the more uh, the tailing edge of the camber airfoil is tilted down, the higher the lift is produced until to a point which is known as stall point, after which there is a sharp decline in lift. This is also represented in this image here, this infographic. As you can see, the more we turn the tailing edge of the wing downwards, we increase the angle of attack and thus the lift. But there is a drawback of drag. But we can even utilize drag in specific cases. Let us see how. This is what a modern wing looks like. It has two additional components, the slat and the flap. These allow us to modify the lift and drag characteristics to beyond what a plain airfoil would have. As you can see in the bottom left plot, an airfoil with slats and flaps has a much higher lift at the same angle of attack as a plane. Also, an airfoil with slats and flaps can push for much higher angles of attack before stalling. Now, coming back to the point of cruise, takeoff, and landing, the three phases of flight. These are the differences in what the wing looks like. At cruise, we try to minimize lift to just enough that that the plane does not fall dip down due to gravity, and does not go up due to additional lift. We completely balance against gravity. For takeoff, we produce additional lift so that the aircraft can take off from the surface towards where it would like to cruise. You can keep an eye on this plot to understand where each of these configurations correspond to. In the landing configuration, we have the flap goes much to the bottom to produce a lot of drag so that the plane can slow down and prepare for landing. This is the point it corresponds to, and in this way we achieve the three phases of flight. And with that, we conclude our presentation on the basics of aerodynamics. Thank you so much. And these are the references we used, including the books as well as YouTube videos that we consider.